Thank you for the introduction, and I'd first like to thank Guillaume and Barbara for giving me a chance to visit Paris again and attend this wonderful venue. I learned a lot yesterday and hope I can continue that exciting discussion today. The work that I'm going to present today has been mostly done by Brent Groholski. Now he's at Smithsonian Institute, and the part of the work was also done by Crystal Catali. She's now in Livermore National Lab. I'm going to mostly talk about phase transformations today in the lowermost mantle. So in 2004, it was reported that the dominant lower mantle phase, which we know that it has a perovskite crystal structure, undergoes phase transformation at about 200 to 400 kilometers above the core mantle boundary. And that generated a lot of excitement because seismologists have long been wondered about the origin of this continuity that was at least locally observed at the similar depth range. But we went through pretty interesting and exciting exercise over 40 to 50 years in geophysics related to the discussions about phase transformations and the seismic discontinuities found between 400 and 700 kilometers, namely mantle transition zone. And through that exercise, what we have learned is that to be able to assign a phase transformation to a seismic discontinuity, there are many different properties that you should be able to check through experiment or through observations. First, obviously, your pressure where you see the phase transformation should match with the depth where you found a discontinuity. And second, the phase transformation you observe needs to have small enough thickness. What I mean by thickness is, thermodynamically speaking, the width of mixed phase region. As soon as you put impurities in the system, your system doesn't undergo to phase transformation at single pressure. Instead, thermodynamics teaches us that the phase transformation goes through so-called mixed phase region, where you have both high pressure phase and low pressure phase coexisting together. So this mixed phase region needs to be small enough to generate discontinuity rather than seismic gradient. And obviously, through this exercise, now we know that there are pyrolytic phase transformations that are not observed in seismology, while minerophysicists still believe that those phase transformations should exist in the mantle. And good example is 520 discontinuity and Wasleyite to ringwoodite phase transformations. In 2009, we published a paper basically examining the property of post-perovskite transition with more mantle-related compositional systems. There we look at binary and ternary system in terms of compositions. And here in this diagram shows the depth and different compositions. Here the convention is that the bars represents the pressure range where we observe high pressure and low pressure mixtures, okay? So like I stated before, you go through from low pressure phase pure field to the mixed phase field, and then finally arrive to the high pressure phase field. And I colored the core area or core depth range with gray color throughout this talk, just to distinguish with the mantle region. Here I show our experiment published in 2009, where basically we show that the 10% iron and 10% aluminum expands the mixed phase region to about 400 to 600 kilometers, whereas seismic estimation for the thickness of the D double prime discontinuity is about less than 100 kilometers. So this means that we have about a factor of 4 to 5 mismatch between mineral physics model and seismic observations. This certainly raises an important questions about the post-perovskite transition relevant to the D double prime discontinuity. There are other studies that exist in the literature that can be compared to our results as well. Here I summarize all other results. They seem to be mismatched each other a little bit in terms of where that bar is located and stuff. We physicists still deal with absolute pressure scale issue, so the vertical variation may come from some degree using different pressure scales, and there are other experimental issues. But what is clear in this plot is that both iron and aluminum seems to expand the mixed phase region, and aluminum seems to have a tendency to increase the depth of phase transformation. If you look at the computation, there are some controversial results out there, but you can find 2 results among 3 we presented here matches pretty well with what was observed in the experiment in terms of the depth effect and the broadening effect of different impurities. Blue represents iron and green represents aluminum in this plot. So then, how do we reconcile the observation we made in the laboratory with seismic observations? Well, there's a good example that we need to check. Well, obviously, yesterday, John Broadholt actually proposed one interesting idea to reconcile the broad phase transformations and the seismic observation of sharp boundary in terms of anisotropy. I'm going to present a little different approach today to reconcile that discrepancy here. Here you look at the olivine phase transformation phase diagram. Vertical axis is pressure, so the depth increases along this direction. And the horizontal axis shows magnesium end member and iron end member directions, which basically shows where your composition exists. So when you measure the thickness of the mixed phase region, by the way, this line defines the mixed phase region. In binary and ternary system, you basically read the phase diagram through the vertical line because your total iron content doesn't change throughout the phase transformation. So you measure the thickness to be about 30 kilometers, whereas seismologists have seen that the thickness should be 8 kilometers. So now we have about a factor of 3 to 4 difference between seismic estimations and laboratory experiment. But it was proposed by Irifune in 1998 that you can actually have a way to reconcile this apparent discrepancy. The trick is that, well, it's not exactly the trick. What is important to realize is that there is a background phase. Although majorite, which is a garnet essentially, doesn't undergo the phase transformation, majorite has a tendency to exchange iron with both wasliite and olivine, and the degree which it exchange iron is different. So now, instead of following this vertical line, we should follow this rather tilted line because we need to take into account other phases, other minerals in the system. And what that leads us to do is to estimate the thickness through this line that gives you about 8 kilometers. So that seems to indicate that there's a way to explain the discrepancy in terms of consideration of the mineralogical effect. And in 2009 paper, we already predicted that this type of thing can happen if you have a phase that absorbs iron and give away iron during the phase transformation. For the lowermost mantle, we propose that the ferropericlase is the best candidate to play this type of role in the phase transformation system. But it was a speculation because we didn't have a data at the time. So in the work that I'm going to present today is actual measurements to test these ideas and expand the ideas to the different compositional system that we expect to exist in the mantle. So in this study, we basically examined 3 different mantle systems. Pyrorite, which has been believed to be the average composition of the mantle, and hospagated composition, olivine dominant composition with fewer aluminum than pyrorite, and morph composition, which is essentially the recycled component that might be injected into the lowermost mantle through subducting slab. So they are all different. So a little bit of experimental factor here. We use Sancollis olivine composition, pyritic composition, and morph composition in this experiment. We maintain the same experimental setup as 2009 paper so that we can facilitate direct comparison between our new results and the old results. So And one thing I like to mention here, which has been a development in our side, is to use two different ways to determine the phase boundary. So in 2009 paper, we measured the phase boundary using the traditional method in low-pressure petrology experiment, where you cross the boundary along the compressional directions and decompressional directions. So you cross the boundary from low-pressure phase to high-pressure phase, and then high-pressure phase to low-pressure phase. That gives you some idea about how much kinetic effect that you would have for the phase boundary determination. So that gives you a reasonable estimate for the uncertainty of your measurements. So we thought that is the strength of the measurements. Then we got interesting discussions with other groups who also worked on this issue. And traditionally, over megabars of pressure, because of a lot of limitation, people have used a different method where they actually bring the fresh, unheated sample to a certain pressure range and then heat it up and then look at what type of phase is formed. So the advantage is that because you start with very unstable starting material, there is a hope that it goes into the stable assemblage better than other cases. But over the years, we mineral physicists have learned that in case you have some thermal gradient and pressure gradient, this doesn't necessarily give you the most stable phase you expect. Rather, it could give you the metastable phase. But nevertheless, we decided to take these two approaches and see what type of results we get. So here, I show you the X-ray diffraction. Don't worry about understanding the details. What I try to show you here is that we basically explore three different compositions: pyrite, sand, color, olivine, morph. And the blue represents the pure perovskite, and the red represents the post-perovskite. So basically, we see a bunch of diffraction lines from the crystal structure that we can use as a fingerprint of different phases. And you can see that the top portion of each diagram shows perovskite pure stability field, and the red shows the stability of pure post-perovskite. And existence of both red and blue obviously means the mixed phase region. And all these X-ray diffraction patterns were measured at in situ high pressure and high temperature during the laser heating experiment at synchrotron. So first, I'd like to compare the composition of pyrite and sand colloidal olivine, or if you wish, hot spaghetti composition that's essentially olivine-dominated rock compositions. So if you look at the iron content expected for perovskite, in pyrite, perovskite is supposed to contain about 10%, and which doesn't change if you change the composition from pyrite to sand colloidal olivine. If you look at aluminum composition, pyrite is supposed to contain about 5% of Al2O3, whereas sand colloidal olivine doesn't allow perovskite to contain any aluminum because starting material doesn't contain any aluminum in it. And in terms of ferropericlase generation, pyrite is supposed to generate about 30% from the system in the lower mantle. Sand colloidal olivine composition produce 50 more percent of ferropericlase. So now you can see the contrast between these two compositions in terms of aluminum compositions and ferropericlase. So those are the two important factors. So now what we try to do is to plug in ferropericlase in the system that was different from what we've done in 2009 and see if ferropericlase can change the thickness of the post-perovskite. And the convention is such that the blue represents, again, the pure perovskite, low pressure phase, and red represents pure post-perovskite, so high pressure phase, and green represents the observation of both high and low pressure phase, namely perovskite and post-perovskite. You can see two different symbols here, triangles and circles. Triangles were the measurements we performed using so-called reversal measurement. What that means is that we synthesize perovskite or post-perovskite and change the pressure, and what happens. That's what we did. That's method 2 that we use. Method 1, which is shown by the circles, just bring up the fresh samples and heat it up and see what happens. So that's a conventional method that was performed by other experimental groups. You can see some mismatches between two groups of data, but they both seem to agree that the thickness should be fairly small in sand color olivine composition. Just to remind you, what we observed in 2009 was 400 to 600 kilometers of the thickness. That is about this distance from 0 and 600 here. So this thickness is really narrow compared to the, what we have observed in 2009. So this clearly indicates that ferropericlase has an impact on the thickening effect of iron. So it effectively regulates the iron effect through element partitioning. And now, like I showed you before, pyritic composition also generates the ferropericlase. So you would expect that pyrite would also have smaller thickness. But in fact, we find it's not the case, as shown by this data. In fact, we have about 400 to 600 kilometers of the thickness. The reason is that there is aluminum that makes the difference. In sand color olivine, we don't have aluminum. Pyrite, we have aluminum. And aluminum has a thickening effect and deepening effect. And there is no other phase that can contain aluminum in pyrite other than perovskite and post-perovskite. So there's no secondary phase that can play the game for the sharpening of the phase boundary. So here I make comparison again. On the left panel, you're seeing ternary binary systems without taking into account the mineralogical effect or secondary minerals. So you see broadening from iron and aluminum. This is computation you already seen about 10 slides ago. And here I summarize the experiments so far we've seen, sand color olivine and pyrite. The convention here is that the dark area represents the underbound, or lower bound, I should say, lower bound of the thickness. And the including dark and bright area, it shows upper bound. So it gives you error bar of our estimate for the thickness. So you can see that the sand color olivine decrease the thickness a lot with respect to iron-bearing system. That's clearly effect from ferropericlase. And for the pyrite, you influence mostly by deepening effect and thickening effect of aluminum, even if you have ferropericlase. So now I'm going to show you the data on morph composition. One thing that distinguishes morph from other composition is the fact that morph contains a lot of aluminum. So here the orange represents the pyrite and green represents morph or basalt. And it turns out that the, in morph you have about factor of 3 to 7 more aluminum than pyrite. So out of the results that I showed already, you might expect, and also we expected, that the aluminum in morph would even increase the thickness and the depth of the post-perovskite more than pyrite. But in fact, we saw a little funny thing here going on. Again, this is our core-mantle boundary. There seems to be a shallowing effect rather than deepening effect. And we do see some thickness here, about up to 300. If you take lower bound, it's about 100 kilometers. But it's definitely smaller than the thickness we observe in pyritic composition, which ranges about 400 to 500 kilometers of the thickness, which seems to be counterintuitive given the fact that morph has more aluminum. So going back, I'm adding morph in the same diagram you saw about 2 or 3 slides ago. Now, even if there is a more aluminum in the system in morph, instead of seeing deepening and the thickening, you see shallowing and, relatively speaking, thinning compared to pyrite. Yet, it is important to go back and check what type of mineralogy you have for the morph composition relative to pyrite and hospogatic systems. So these two were the comparison that I made in the beginning of the talk. Now we're talking about morph. And as you can see, the concentration of magnesium silicate perovskite or post-perovskite is significantly low. It's about 30%, whereas your pyritic mantle produces about 70 to 80%. And more importantly, you have other secondary phases that didn't exist in hosphagite or pyrite, which are silica, SiO2, or stishovite, and the so-called calcium ferrite phase, and also calcium perovskite. But don't worry about understanding these individuals. What is important is that silica contains some iron, aluminum, I'm sorry, and calcium ferrite type phase contains both aluminum and iron. So these are two good candidates to influence the thickness of the post-perovskite transition. So now I'm laying out the idea that we have to understand this rather puzzling experience. Shallowing of Habsburgite is more or less understandable in terms of ferropericlase effect, but shallowing of Morve and thinning of Morve is rather surprising. And the top axis shows less aluminum for the left-hand direction, and the right-hand direction, you have more aluminum. I'm comparing three different systems, Habsburgitic, pyrolytic, and Morve systems. I put up the mineralogy differences here and different elements here. Like I said in the beginning, iron and aluminum seems to have both thickening effect if they are not controlled. Habsburgite, we don't have aluminum, so don't worry about aluminum, but we do have ferropericlase that is capable of decreasing the thickness. So that leads to the sharper boundary in post-perovskite. Pyrite has ferropericlase, so it controls iron perhaps, but it doesn't have a phase that can control aluminum, and that leads to the larger thickness and the deeper depth. And finally, for Morve, even if we have more aluminum than any other systems, because it contains secondary phase that is capable of containing aluminum and iron, we believe that those secondary minerals, well, they are no longer secondary minerals, I shouldn't say that, have a controlling effect for the thickening of aluminum and aluminum. So this slide summarizes what we have seen so far. It seems that mineralogical effect is quite big for understanding the thickness of the post-perovskite discontinuity among different systems. So now I'm going to talk a little bit about other systems. This is 21st slide. So I'm going to finish pretty soon. So now we look at other minerals in the mantle. Obviously, mantle may be silica undersaturated and MgO oversaturated, the normal mantle. But from the talk we've seen yesterday, there is a possibility of injecting silica-rich material to the bottom of the mantle through subduction, for example. So we could have Morve. As I showed you a few slides ago, Morve can contain silica, and sediment can transport it down to the core mantle boundary that exists in the surface, ocean bottom part of the subducting slab. And there are some suggestions that the reaction between core material and mantle material may produce some free silica. So if you assume that silica might exist there, it might be worthwhile to check what's going on with silica. And in fact, over 20 years, mineral physicists have observed the phase transformation in silica at mantle-related pressures from modified spinel structure to so-called sapphire structure. Sapphire is a mineral that was observed in nature remarkably, although the stability field is really high. So we determined that boundary. What we think we did make improvement in this phase diagram is that we use same pressure scale and same experimental setup. So it facilitates the comparison between our post-perovskite results and this phase transformation boundary. So the red here line shows the where that silica boundary locates with respect to the post-perovskite transition in Morve composition. So this shows you that the post-perovskite transition is, relatively speaking, shallower, and the silica boundary is, relatively speaking, deeper. Well, it's debatable whether this the silica boundary may exist in the mantle or not, because it's so close to the core mantle boundary. But for the sake of discussion, let's, at the moment, assumes that it may exist in the mantle, but what is clear for us is that it should exist deeper than the post-perovskite transition. Although I don't show you the data, we found that the bulk sound speed shouldn't change much across the this silica phase transformation. But there's an interesting theoretical estimate. There are actually two, basically saying that shear velocity should decrease across this boundary rather than increase. Just reminds you, post-perovskite transformation, we expect that the shear wave velocity increases about 2 to 3%. In this case, they estimated that it'll decrease by 1 or 2%. So that gives us a pretty interesting case to interpret some of the observations that has been made. So in some area in the core mantle boundary region, seismologists have seen this funny structure where you see increase in shear velocity and then decrease in the shear velocity at the deeper depth. It has been traditionally interpreted, not traditionally, but last 5 to 10 years, it's been interpreted as a double crossing of the post-perovskite boundary with the geotherm that is steep in this region because of the nature of the thermal boundary layer. So it gives you a pretty interesting predictions that this type of double crossing would give you negative correlation between the top boundary and the bottom boundary. Instead, if you have silica-rich material, and if you happen to have both perovskite transformation systems and silica transformation systems in the same region, what you can hypothesize is that you're crossing the boundary twice through geotherm, and what would give you is that because their Clapeyron slope is nearly similar to each other and positive, you would expect to have positive correlation between these two boundaries. What that gives you is that the double crossing idea would remain as a very interesting probe for the temperature in the lowermost mantle. If this scenario is applicable for some of the observations, I don't know whether it exists or not, then it could potentially give you chemical probe for the seismologist to trace where the recycled materials may end up being in the coal mantle boundary. Obviously, there are many things needs to be, examined in experiment. First, we need to better understand the element partitioning among different minerals, and that's probably the take-home message of my talk today. And second, we are in the process of exploring other compositions. Today, I show mostly recycled component-related compositions. We're in the process of learning more about so-called primitive or ancient materials like chondritic compositions and solidified mantle melt compositions and stuff like that. And finally, I think that we are in the stage where we really need to check again about our knowledge on mantle mineralogy, because it seems that it might have a very important influences in many of the properties we have discussed so far. So thank you so much for the attention.